Hey students of statics, it's Dr. Dan. And today's example we're going to take a look at is a three-dimensional moment around a point problem. And we're going to talk a little bit at the end about how moments at a point relate to moments along a line as far as how their components interact. So here is our situation. We have a wrench, okay? So you could think of this as like a wrench along here, starting at B going over the x-axis, and maybe an extension going over here to point A. So you can think the nuts over here sitting maybe at point O. And we are going to apply a force with the components of 500 in the x-axis, negative 400 downward, and 200 in the z. Okay, so we can take a look at this a little bit in this three-dimensional view, right? So there's the force is downward, angling out in the z, and angling over to the right in the x, right? So that's our force. Now, hopefully, as you take a look at this, you could use your right-hand rule, either slide and curl or three-finger, and think about doing that right-hand rule, starting here at the origin, right? Your moment arm, your position vector. We're going to take a moment around point O, so that moment arm will start at O, extend out here to B. And then we're going to cross that into this force vector here. Now, I've got this GeoGebra Interactive all queued up, so I can actually show us the answer. Boom. All right, so here is our answer for this problem. Zoom in here just a touch. Again, here's our R vector, right? That R vector going from O over here to B. And as you did that, extending your right hand fingers along OB, curling them down here into the force. You should have got your thumb going up here to the right, right? It's to the right, it's back. The components there are 160, positive 140, and negative 120 in the Z. So the negative 120 in the Z is going back in the page, Y going up, and then also positive X here. Okay, so we're gonna go ahead and work through this using a determinant. Here we go. So to start with, we need to draw in our moment arm. Okay, this moment arm connects point O over here to point B, so I could label this here as ROB. And it's going to actually have the same coordinates as point B, right? Because it goes from the origin over to point B. So if you subtract these coordinates at B minus 0, 0, 0 over there at the origin, we'd actually have the same exact vector components. The force components are listed here, so we actually have all the information we need to get going on this problem. All right, and again, our problem statement here, what we're being asked to do is to find our moment about point O from this given force. Okay, so we know from our notes from the class that the sum of moments around any point is a vector, and we get that from our cross product. Okay, this is gonna be the cross product of ROB. We're gonna cross that with our force, the single force in the problem. So we know ROB, we know the force. So let's go ahead and put these things into our equation. Sum of moments about point O. And we know that we use a determinant to compute this cross product. We need an I hat and a J hat and a K hat in the top row. Those are not optional. Those are actually the reason that we end up with a vector answer as opposed to some kind of a scalar answer. And then we get into the position vector components there. So 0.3 meters in the I, 0 vertically in the J, and 0.4 in the K. Again, all those are in meters. And then we have the force components of 500 newtons, negative 400 newtons, and 200 newtons. Now, I know there's multiple ways that you can do cross products. I like to do the augmented matrix and then do diagonals. I think it's really explicit on exactly why these work for cross products. So I'm going to recopy the first two columns, 0.3 and 0 and 500 and negative 400, right? Again, just recopying these two columns right here. Then we start looking at diagonals. Okay, so for positive diagonals, I have an I hat positive diagonal here, here, and here. We'll go ahead and circle that one. I have a non-zero J hat diagonal with the 0.4 and the 500. And then I have a non-zero K hat with the 0.3 and the negative 400. Okay, so three non-zero positive diagonals. And then coming back on the negative diagonals, I have this one with the J hat. I have another one here with that I hat. Now that third diagonal with the K hat is a 0 in there, so that one would not register. So then to go ahead and write out these terms, we have that the sum of moments around point O, again, it's a vector, Pulling my I hat term first, I have on the negative slant, so let's throw that negative out front, negative 0.4 times negative 400. And again, that's in the I hat. And then for the j hat term, I have to do this on 3 lines here, so make sure I have plenty of room. The j hat term, we have 2 of them. On the positive slant, we have positive 0.4 times 500. Put a bracket out front here because I have 2 of those terms. And then on the negative slope there, we have minus 0.3. Again, the negative from the negative slope coming back to the left. And then that's times 200. And those are both times j hat. And then for the k hat term, there's just one of those. It's a positive slope. And so that's going to be 0.3 times negative 400. Again, that's in the k hat. So if we bring those together, the sum of moments about 0.0, running through our calculator, we end up with hard bracket here to indicate that they're vector components, 160, 140, and the final one here, negative 120. And the units, we multiplied newtons times meters, and so there is our sum of moments around 0.0. Okay, so we created a position vector connecting our point of interest to the line of action of the force. We then inserted this information as well as the force components into a determinant, and then finally worked through that determinant. There are multiple ways you can work through determinants. We chose on this problem to work through an augmented matrix, which basically means to recopy those first 2 columns and then use diagonals. You get this exact same answer if you use kind of the box and holdover method that many of you might have learned in calculus, but I do like this augmented matrix. So then if we followed up this question with one more simple question, and the follow-up question we have is how much of this moment, right, the sum of moments about 0.0 is about the x-axis. Now the reason I would ask a question like this is because if this was a nut sitting over here at 0.0 and we're trying to remove that nut with this wrench, this is actually the moment that we're looking for. This is the useful moment that would loosen that nut. With your right hand rule, you could wrap your fingers around that x-axis, pointing over to the right along the x with your thumb, showing that the rotation in that direction would give you a moment, rotation of that nut would remove it to the left. And so all we have to do to answer this question is simply look at these 3 components. Our answer sits right here. Technically, if we wanted to, we could actually dot this answer with the unit vector along the x-axis. So I could write this as, the scalar moment about 0.0 along the x-axis. We could also maybe call that MOX. That would actually work. So what we do with that is we take this sum of moments around 0.0 as a vector we just found, and we dot that with I hat. Right, and I hat is 1, 0, 0. And so effectively what that's going to do is it's, when you think about what a dot product does, it's going to multiply our x component of the moment times 1, the y component times 0, the z component times 0, and all we're left is the x. Right, so I could write the answer here, the MOX is equal to 160 Newton meters. Right, and again, that's the amount of the moment directed along the x-axis. This is actually the useful moment that you could use to remove that nut using this wrench. If we had additional forces, you could also have additional moment arms, additional forces. Basically, that gives you additional determinants that we would include up earlier in the problem. Thank you so much for your attention today. I hope this was a useful setup in seeing how you take 3-dimensional moments. I hope you're having a good one. Bye-bye.